Hello and welcome back. In this video we are going to continue the discussion on the topic of spintronics. In the previous video, we discussed magnetization dynamics and magnetization switching. We showed that the Landau-Lifshitz-Gilbert equation provides an accurate description of switching dynamics of a nanomagnet subjected to an external magnetic fields. The external magnetic field exerts a conservative torque on the magnetization, which when sufficiently strong, destabilizes one of the metastable magnetization states in systems with uniaxial magnetic anisotropy. In today's video, we are going to explore novel ways of generating torque on a magnetization that does not rely on external magnetic fields. Such field-free torques that we're going to discuss today arise from quantum mechanical effects and are induced by a flow of spin currents into or out of a magnetic element. We are going to divide the video into three main parts: the introduction, the physics behind the spin transfer torque effect, and magnetization switching induced by spin transfer torque. With that, we hope to provide an intuitive understanding of this phenomenon and its importance. Let's get started. Part 1. Introduction to spin transfer torque. We saw that in MRAMs, one can write binary information in MTJ devices by means of magnetic field switching. Here, writing currents are applied to the specific bit line and word line whose intersection point coincides with the location of the MTJ device one wants to switch. Then, the local Ørsted field generated by the currents cause a torque on the magnetization of the free layer of the MTJ, and magnetization switching might take place if the field is strong enough. A detailed schematic is shown on the right. Although this method provides a systematic way of writing information in MRAMs, the Ørsted field generated to cause a switching event in a particular MTJ device can also influence the adjacent MTJ devices due to its spatially extended nature. This process might induce undesirable switching events in neighboring MTJs, placing severe limitations to the writing process in MRAMs with large bit density. In addition, this switching mechanism also suffers from energy inefficiency. That is, large amounts of currents are necessary to induce strong enough Ørsted fields to cause switching. Hence, a switching mechanism that can address individual MTJ devices without disturbing its neighboring bits, while being energy efficient, is highly desirable for applications in MRAM. Much more promising switching mechanisms for MRAMs are those that rely on the so-called current-induced torques. Here, the right current applied to the bit line passes through the MTJ device, as shown in the right figure. The flow of current through the MTJ gives rise to a torque acting on the magnetization of the free layer by a quantum mechanical phenomenon known as spin transfer torque. Such a spin transfer torque mechanism provides a more efficient way to writing binary information in MRAMs. Thus, memories that utilize such switching mechanism are referred to as STT MRAMs, a short for spin transfer torque MRAMs. The spin transfer torque effect was theoretically predicted by John Slonczewski and Luke Berger in the 90s. The basic idea of spin transfer torque is as follows: the current passing through the MTJ device is initially unpolarized. That is, the electron spin orientations are randomly distributed, such that no net spin polarization exists. However, as the unpolarized current passes through the first ferromagnetic layer, the fixed layer, it gets spin polarized along the direction of the magnetization. Now, the flow of spin polarized electrons into a second misaligned ferromagnetic layer results in a transfer of spin angular momentum to the local magnetization via exchange interactions. If enough spin angular momentum is transferred in this process, it can excite magnetization dynamics of the free layer, and even cause magnetization switching. This, in a nutshell, is how an electric current can induce switching of a ferromagnetic layer. Today, current-induced switching via spin transfer torque is already a well-established phenomenon. The plot shows experimental confirmation of spin transfer torque switching. Let's assume that the initial configuration for the MTJ at zero applied voltage is in the high resistance state, as highlighted with a yellow circle. This corresponds to the MTJ being in the antiparallel configuration. If one passes a current through the MTJ device by applying a negative voltage, a sudden discontinuous change in resistance is observed around 300 mV. This amount to a current of about 25 microamps passing through the MTJ in the experiment. The sudden change in resistance signifies a transition from a high resistance state to a low resistance state. It corresponds to a transition from the antiparallel magnetization configuration to a parallel configuration. Hence, magnetization switching has been induced by means of an electrical current and not by magnetic fields. If now one was to switch the configuration of the MTJ from parallel to antiparallel configuration, all that is needed in this case is to pass a current in the opposite direction. To see this, we now start at the low resistance state at zero bias voltage, as highlighted by the yellow circle. By applying positive voltages now, it is observed that there's a critical value where the resistance suddenly jumps from a low value to a larger value. Here, this corresponds to a voltage of about 600 mV, or a current of 52 microamps. Hence, by applying a current in the opposite direction, one can attain switching from a low resistance parallel configuration to the high resistance antiparallel configuration. In the remainder of this video, we are going to provide a description of the phenomenology behind this effect. Part 2. The physics behind the spin transfer torque. To understand how spin transfer torque works, we begin by recalling the conservation of charge and current continuity in electron systems. The quantum mechanical analog of the classical charge continuity equation is the continuity equation for the conservation of probability density. The electron number density, or probability density, at a given spatial location, R, is simply the absolute square of the wave function. Since electrons also have spin, we sum the probabilities for each spin state, as explicitly shown. From this definition, the continuity equation expressing conservation of the electron number density is as follows. The continuity equation tells us that the rate of change of the electron number density at position R equals the divergence of a vector quantity J. This vector J characterizes the flow of probability density into or out of R. Therefore, J is the current associated with the electron number density. That is, J is the probability current density or electron number current density. Its explicit expression in terms of the electron wave function is given as follows. Hence, any variation in the number density at location R is associated with a flow of probability density. This is precisely what a local conservation law tells us. Probability density cannot be destroyed or created from nothing. Any change in probability density is associated with an inflow or outflow that accounts for the variation. The continuity equation shown here provides an accurate description of charge conservation. Because each electron carry a quantum of charge, conservation of electron number is equivalent to the conservation of charge. However, does charge conservation also mean spin conservation? After all, electrons also carry spin. Let's have a look at it. To answer this question, we first need a definition for the spin density. As a first attempt, we can define the spin density as the probability density for spin-up electrons minus the probability density of spin-down electrons. The factor of h bar over 2 accounts for the dimension of angular momentum. This defines only the spins oriented along the z direction. To account for all the other components of spin, a generalization of the formula is required. The full spin density can be defined as shown here. Note that the vector of Pauli matrices accounts for all components of the spin density. We are now in a position to show the continuity equation for spin density. So far, the analysis already suggests a big distinction between conservation of charge and spin. In the case of charge conservation, the continuity equation describes the conservation of a scalar quantity. Now, the spin continuity equation must describe the conservation of a vector quantity. Let's see what it looks like and the consequences of this important observation. The continuity equation for the spin density is highlighted in the left yellow box. It tells us that the rate of change of spin density and location R equals the divergence of a quantity Q that describes a flow into or out of that location. The quantity Q is, therefore, the spin current density. Its definition is highlighted in the right yellow box. The big difference now is that the spin current is a tensor quantity, as apparent from the tensor product in its definition. This is due to the fact that one needs to define a velocity direction as well as a spin direction to make sense of a spin current. Note that the continuity equation for charge and spin densities look exactly the same in form. The only distinction is in the definition of densities and currents. But how would the continuity equations look like in a ferromagnetic material? This is a crucial question for the spin transfer torque physics. In a ferromagnetic material, there is an intrinsic exchange field that is responsible for the finite magnetization. Let's now consider how the conservation laws for charge and spin gets modified in the presence of an exchange field. The charge continuity equation looks the same as before. This is because the exchange field does not couple to the charge degree of freedom. Hence, the total charge density and charge currents definitions won't be affected in a ferromagnetic materials. The continuity equation for spin, however, is modified. Now, there is an extra term in the right-hand side of the equation that only exists if the spin density and the exchange field are not collinear. The appearance of this extra term is due to the fact that the spin degree of freedom of electrons couple to the exchange field of the ferromagnetic material. The extra term in the continuity equation for spin is a torque term. It describes the torque exerted on the spin density due to the exchange field. In steady state, where nothing varies in time and the time derivatives vanished, the charge and spin densities continuity equations inside a ferromagnet are shown above. The zero divergence of the charge current says that the total charge current flowing into a volume of space must equal the total flow of charge out of that volume if there is no charge accumulating within. Hence, incoming current, J in, must equal the outgoing current, J out. For spin current, the extra torque term changes the picture substantially. The steady state equation says that the total spin current flowing into a volume of space does not necessarily equal the total spin current flowing out of that volume even if the magnitude of the total spin density is not changing. The direction of the incoming spins can change due to the exchange field torque within the volume. Hence, the outgoing spin current can have a different spin direction due to the exchange field torque. This can be illustrated in junctions composed of non-magnetic and ferromagnetic materials, like the cartoon shown below. Consider the injection of charge and spin currents from a non-magnetic material into a magnetic material. The injected electrons into the magnetic materials will have a spin current polarized along the exchange field of the magnetic material, after it propagates some distance into the magnetic materials. As we previously discussed, any misalignment between the electron spin and the exchange field will generate a non-zero exchange torque. Hence, the spin current at the non-magnetic end is not the same as the spin current in the magnetic material end. The imbalance of the spin currents at the two ends is due to the non-zero exchange field torque. From here, we see that a magnetic material is equivalent to a spin polarizer, where the direction of spins of the outgoing spin current is determined by the magnetization direction. The polarization mechanism is the exchange torque. Let's explore in more microscopic detail how the scattering of electrons with different spin polarizations take place in heterostructures composed of magnetic and non-magnetic materials. The color maps display the reflection probability of spin-up and spin-down electrons at the interface between copper and cobalt. A sketch of the heterostructure is shown to the right. The electron incident from the copper layer propagates along the z direction towards cobalt and is scattered at the interface located at z equals 0. The system is assumed to be translationally invariant along x and y direction. Hence, the momenta kx and ky are good quantum numbers. The color maps show the probability that an electron incoming from the copper layer will reflect for all in plane momenta kx and ky. The left color map refers to the reflection probability for up spins, while the right color map refers to the reflection probability for down spins. The first important point to notice is that the color maps are distinct, which means that different spin states have different reflection probabilities. That is due to the fact that the spin properties are different inside cobalt, which is magnetic. To emphasize this important feature, we illustrate the scattering of spin-up and spin-down electrons at a given momenta. We focus on the momentum highlighted by a small red region in the color maps. At this specific momenta, we see that the reflection probability for spin-up electrons is 0 while the reflection probability for spin-down electrons is 1. The scattering at this momentum value is depicted on the right. For spin-up electrons, they do not scatter at all at the interface, as shown in the top schematic figure. That is, the electron fully transmit to the cobalt side because its reflection probability is 0. For spin-down electrons, they fully scatter back to the copper side because their reflection probability is 1. Thus, the scattering of electrons at the copper-cobalt interface is spin selective. What if the incoming spin is neither up or down, but instead its spin orientation is tilted in relation to the z direction? That is, what if the incoming spin orientation is misaligned with the magnetization direction, as shown in the figure? Let's assume the incoming spins are oriented along the y direction, for simplicity. Its associated spin current is written explicitly. The first vector is the spin direction, oriented along y. The second vector is the velocity direction, which is along x. We can easily figure out the scattering probability by recalling that a spin along the y direction can be written as a coherent superposition of up and down spins along the z direction as shown. Thus, we can now apply the same line of reasoning as before. The result is summarized here, where we can see that only the spin-up portion of the incident state transmits into the cobalt side, while the spin-down portion of the incident state reflects back into the copper side. The reflected and transmitted spin currents are also written explicitly. In summary, the total spin current leaving the interface is different from the total spin current arriving at the interface. The spin current arriving at the interface has spin direction along y. The spin current leaving the interface has spin direction along z. This is a unique consequence of the spin-dependent reflection probability discussed previously. From the perspective of what we discussed previously in relation to the continuity equation for spins, a difference in incoming and outgoing spin currents mean that there is a torque acting on the spins due to the exchange field. Here, the torque is caused by the magnetization of cobalt. But if the magnetization exerts a torque on the current carrying spins, there should also exist a back torque acting on the magnetization due to the incoming spins. This torque should be equal and opposite due to conservation of total spin angular momentum in the system. The torque acting on the magnetization is called spin transfer torque. Its magnitude can be computed from the difference between spin current leaving and arriving at the interface by taking its dot product with the normal to the interface area element as shown in yellow box. In summary, spin-dependent interface reflection is a mechanism through which an incoming spin current can exert a torque on the magnetization of a magnetic material. The lost spin component of the injected spin current is transferred to the interface magnetization due to total angular momentum conservation. It is important to emphasize that there are other mechanisms for spin transfer torque. The interfacial torque due to spin-dependent reflection is just one of them. Another spin transfer mechanism is based on the concept of spin dephasing. Here, the transmitted spin precesses around the exchange field of the magnetic material, as illustrated in the right sketch. But the precessional rate depends fundamentally on the wave vector of the incoming and scattered electrons. The spin of electrons with different momenta will dephase. As a result, the spin current deep inside the magnet is different from the injected one. the imbalance in the spin current is being transferred to the magnetization, causing a torque on it. It is worth noticing that the final torque is transverse to the magnetization regardless of the mechanism for spin transfer. Although illustrated by means of a simple model, this is a general feature of spin transfer torque physics. Thus, the total spin transfer torque is written in terms of two components mutually orthogonal to each other and to the magnetization M. These components are referred to as field-like and damping-like torque components. The nomenclature is due to the observation that the field-like component tends to cause precession of the magnetization, analogous to the torque due to a magnetic field, while the second component is dissipative, analogous to the torque due to intrinsic damping. Now we understand the origin and shape of spin transfer torque. Let's investigate its impact on the magnetization dynamics. Part 3. Magnetization switching induced by spin transfer torque. Our starting point is the LLG equation. For an overview on the LLG and magnetization dynamics, we refer you to our previous video on the topic. We consider a magnetic element with uniaxial anisotropy, whose anisotropy field is explicitly given here. The magnetic layer has thickness d, as schematically shown in the figure. The incoming spin current has spin orientation along the z direction. The new feature now is the presence of the spin transfer torque on the right-hand side of the LLG equation. The spin transfer torque is composed of the field-like and damping-like components, as described previously. Note that this is different from what we saw in our previous video when we analyzed the dynamics due to an external magnetic field. In that case, we only had an additional field-like torque component acting on the magnetization. Here, the spin transfer torque mechanism naturally provides a damping-like component in addition to the field-like. We note that this is the most general way of writing the torque, as two components transversal to the magnetization. The torque cannot be collinear with the magnetization, as that will not preserve the magnitude of the magnetization. As we will see, the artificial damping component due to spin transfer substantially modifies the magnetization dynamics. To intuitively understand the impact of spin transfer torque on the magnetization dynamics, we rewrite the LLG equation in a simpler form. The simpler form, also known as Landau-Lifshitz form, is obtained by replacing the time derivative of the unit magnetization vector in the intrinsic damping term and simplifying the expression. The equation transforms into the following. Note that the LLG equation in the Landau-Lifshitz form doesn't have a time derivative term on the right-hand side. However, there are new mixing terms that now appears. By replacing the anisotropy torque and spin transfer torque in terms of field-like and damping-like components, and making explicit that the H effective is along z direction, we arrived at the simplified equation as follows. Note that the new form of the LLG equation is much simpler than what we had seen previously. It only has two terms on the right-hand side. The first one is a conservative torque and the second one is a dissipative torque. The big difference now is that the conservative torque due to anisotropy is renormalized by the presence of field-like and damping-like spin transfer torque components, as shown explicitly. The same is true for the dissipative damping torque, as shown in the lower equation. Hence, we can interpret this result by saying that the presence of spin transfer torques renormalize the conservative and dissipative torques. This is an incredible finding. In the original LLG equation, the dissipative damping torque is an intrinsic property of the magnetic element. As such, it cannot be controlled by external means. Now, with the presence of spin transfer torque, the total dissipative torque gets renormalized by the field-like and damping-like components. Since the spin transfer torque is produced by electrical currents, as explained previously, we now have the possibility of controlling the total effective dissipative torque of the magnetic layer. Hence, there is now the possibility of inducing switching of the magnetic layer via damping-like torque. Let's investigate that in more details. Before we proceed, we note that the total effective damping torque can vanish for particular strengths of damping-like and field-like spin transfer torque components. Under this specific condition, the LLG equation reduces to the following. Hence, whenever the damping-like spin transfer torque reaches this critical value, the total dissipation in the system vanishes. The interpretation is that while the intrinsic damping of the magnetic layer dissipates energy, the spin transfer torque can pump energy into the system. Hence, there is a point where the amount of energy pumped into the magnetization balances the dissipation. This happens precisely at the critical value shown here. With this information at hand, let's finally investigate the magnetization switching induced by spin transfer torque. We shall analyze three situations of increasing magnitude of the damping-like spin transfer torque strength from smaller to larger than the critical value magnitudes. In the first situation, we consider the magnetization dynamics induced by spin transfer torque with a damping-like magnitude smaller than the critical value. The initial magnetization orientation lies close to the north pole of the unit sphere. As we can see, the magnetization relaxes towards the positive z-axis and no switching event takes place. This is the scenario where the energy dissipation due to intrinsic damping is stronger than the energy pumped into the magnet by the spin transfer torque. Let's now see what happens when we increase the magnitude of the spin transfer torque. This is achieved by increasing the spin current density being injected into the magnetic layer. Here, we show a situation where the damping-like spin transfer torque reaches the critical value. In this situation, the energy dissipation due to intrinsic damping is perfectly balanced by the energy pumped into the magnetization by the damping-like spin transfer torque component. As we saw previously, the total effective damping torque vanishes here. Since there is still a total effective conservative field torque acting on the magnetization, the system is forced to stay in a precessional state. Therefore, spin transfer torque can induce stable precessional states in magnetic elements. This finding is of extreme importance for nano-oscillators based on magnetic materials. Let's now go one step beyond and consider the case where the damping-like spin transfer torque becomes larger than the critical value. This is achieved by further increasing the injected spin current density. In this case, the dissipation of energy due to intrinsic damping is overwhelmed by the energy pumped into the magnetization by the spin transfer torque. Thus, full magnetization switching takes place, as shown by the simulation. Here, the magnetization is initially gaining more energy than it is losing. Hence, its precessional angle must increase, which eventually leads to switching. Note that this is the case whenever the damping-like spin transfer torque changes the sign of the intrinsic damping. That is, it only happens at the north hemisphere. At the south hemisphere, the intrinsic damping torque changes sign due to the uniaxial nature of the anisotropy torque. Hence, the damping-like spin transfer torque and the intrinsic damping now have the same sign, which means that the magnetization is now losing energy. Hence, the precessional angles decreases all the way down to zero. That final configuration is, therefore, a fully switched magnetization oriented at -z. This concluded our discussion of spin transfer torque. In this video, we presented the complete picture of what is spin transfer torque and why it is important, what is the physics behind this effect, and, finally, how it can be used to switching a magnetization. In the next video, we will discuss another current-induced torque mechanism, the so-called spin orbit torque. Stay tuned, and subscribe, so you will be notified of our future episodes.